Hello and welcome to this review of current as it's going to appear on the MCAT. In this video, we'll be delving into the basic definitions of what current actually is, how it travels in order for us to use it to our own ends, how we measure it, and then some laws that govern its behavior within a circuit. Our goal here then is to develop an understanding of the often elusive concept of current and to be able to apply that understanding to MCAT-style problem solving, as would be required on problems like the one you see at the bottom of your screen. The first thing to note is the most basic definition of current, which is that it is our term for referring to moving charge. The second thing to note is the convention inherent in this definition. It is not just the movement of charge, it is, by convention, the movement of positive charge. So current moves in the direction opposite the flow of electrons, as strange as that may sound. More often than not, you'll be dealing with the specific case of current flowing through a circuit. In a circuit then, current is the flow of charge towards the negative terminal through a conducting material, most often a wire. Now let's talk more about those conducting materials themselves. How well a material is able to hold and carry charge is referred to as its conductivity. Now conductance, which refers specifically to the ability of an element of a circuit to carry charge, is the inverse of resistance, which means that the less resistant an element is, the better it conducts current. This ability is measured in Siemens, capital S. For the purpose of the MCAT, you need to be aware of two types of conductivity. The first is metallic conductivity. A material allowing free flow of electrons within it is called a conductor, and because of their atomic properties, metals make great conductors. You may remember from your Gen Chem review that metals can relatively easily lose an electron or two as they are not bound tightly to the nucleus. So when a lattice of metal ions is formed, the charge density of those loosely bound electrons is shared between nuclei, essentially dictating that there is a sea of communal electrons which can move freely. And we saw only moments ago that moving charge equals current. The second type of conductivity to be familiar with is electrolytic conductivity. The guiding principle here is more or less the same as it was for metallic conductivity, except the C being referred to is somewhat more literal. An aqueous solution with very few dissolved ions will necessarily have relatively little moving charge. Conversely, a solution with high molarity or lots of dissolved ions will be a sea of moving charge. As such, concentration and conductivity are directly related to one another. However, it is critical to note that non-ionic species do not act as conductors, so increasing their concentration does not increase a solution's conductivity. That's our extensive definition of current and how it works. Now let's elucidate how it's measured. Because current, again, is the flow of charge, the more charge that's flowing, the more current there is. That's what this formula dictates to us. The more charge passing a certain point per unit time, the greater the magnitude of I, current. Our unit for current is thus coulombs of positive charge per second, or amperes, more commonly called amps. On the MCAT, you will be dealing almost exclusively with direct current, where the charge flows in only one direction. You may also see alternating current. It's rare, but it could show up, and it is characterized by the direction of flow changing periodically. Our picture of current would be incomplete without consideration of some intertwining concepts here. What inspires charge to move in a circuit is the potential difference. The positive charge seeks to move away from the positively charged terminal to the negatively charged terminal. More properly, the electrons flow to the positive terminal. But keep that current convention in mind. We care about the direction positive charge should flow in. When the positive and negative terminal are not connected by a conductor and charge doesn't actually move, the potential difference between the terminals of the battery, which would motivate electrons to move, is called the electromotive force, conveniently enough. Now let's investigate two laws which govern the behavior of moving charge when the circuit is closed and those terminals are connected. The important underlying principle which you must note is that energy and charge are conserved in any circuit you see on the MCAT unless you are explicitly told otherwise. From this guiding principle, we get Kirchhoff's laws. The first is the junction rule, which says that the magnitude of current flowing into any point must equal the amount of current leaving that point. When that point is a junction, the principle holds. In this circuit, we see 10 coulombs per second entering this junction. So naturally, there must be 10 coulombs per second leaving that point, otherwise energy would necessarily be entering or leaving the circuit. We see that I2 is 2.5 amps, so that means that I3 must make up the difference here. Its magnitude must be 7.5 amps. Kirchhoff's second rule is the loop rule. It tells us that the voltage from the source, or the battery, is equal to the voltage drop across the circuit. Put differently, all the energy supplied to the moving charges by the battery is consumed by those charges in one trip around the circuit. So in any circuit, such as the one at the bottom of your screen, the elements of the circuit must dissipate x joules of energy per coulomb of charge, where x is the total voltage supplied to the circuit. And in this case,
X is 6 volts.
That is the sum total of our exploration of current in this video, so let's check out a couple of practice questions. Give this first one a try. Remembering and applying Kirchhoff's junction rule will win you the point on this question. Let's analyze this circuit junction by junction. If an 11 amp current enters the junction after point A, an 11 amp current split two ways must leave it. A 5 amp current flows down the screen to point B, so 6 amps of current flow up the screen to that next junction. A 4 amp current flows into this point from point C, and we just figured out that a 6 amp current flows into it from point A, so it must be a 10 amp current flowing through point D. Let's keep the currents in our neural circuits flowing and give question number 2 a shot. Remembering that the conductivity of an electrolytic solution depends upon its concentration, we can go on and dissect our answer choices to find the ionic solution with greatest concentration. Option A, the salt magnesium chloride, dissociates into 3 moles of solute per mole of solid added into solution. That means that 4.5 moles of solute result from option A. Option C is another salt, but sodium chloride only dissolves into 2 moles of solute per mole of solid, for a total of 4 moles. This can't be our answer. Similarly, we can compare B and D, sulfuric acid and acetic acid. Acetic acid only dissociates into 2 particles like sodium chloride, so it can't be the answer. We're down to A and B. Sulfuric acid is a strong acid, so it dissociates completely in water. The HSO4, or bisulfate ion, however, is a weak acid and does not dissolve completely in water. So the resultant concentration will be greater than 3 molar because there is that second proton dissociating, but it will be less than 4.5 molar because that last proton does not dissociate completely. So A is our answer. In this video, we first defined current as the flow of positive charge, an important convention to keep straight. We proceeded to identify what current flows through and how those materials or solutions actually conduct that flowing charge. Next, we started to put some names and numbers to the concepts by applying the current formula I equals Q over T, or charge per unit time. Lastly, we applied 2 laws delineated by Kirchhoff that describe the behavior of current flowing through a circuit, the junction rule and the loop rule. Thanks for watching through this video on current. It is a very important topic to have a strong conceptual grasp of, as it comes up over and over and over throughout the physical sciences on the MCAT. So make sure you stay current with your knowledge of current.